Hello, welcome again. Today we're going to talk about section 4.4 from our geometry text, proving triangles congruent using SSS and SAS. SSS stands for side, 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 and we have congruence postulate. The side, side, side postulate states if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. Showing a picture here, states if MN is congruent to QR and NP is congruent to RS and PM is congruent to SQ, then triangle MNP and is congruent to QRS. So we know that we can prove triangles congruent or figures congruent in general if we have all of their sides and all of their angles congruent. Here we're making the statement that we have a postulate that states if we show just that all three sides are congruent, then all of the angles are congruent. Kind of doing a little informal explanation of that, we know that if we have a side congruent, for instance NP here and RS, that the angles then across from them, the opposite angles, angle M and angle Q, well, those angles must be the same, okay, because you can only construct the angles one way to get that side length. So using that same logic, then we know that angle N and angle R are congruent, and the same thing with P and S. So therefore we have all angles and all sides being congruent, which is the definition of having congruent triangles or congruent figures for that matter. So this does hold true, and we could write a formal proof, but we're just going to trust previous mathematicians on this one. Alright, let's show this congruence postulate. The statement says prove PQW is congruent to triangle TSW. Again, all proofs from the picture. We can note that all the sides PQ congruent to ST, QW congruent to WS, PW congruent to TW, with three sides in the left triangle being congruent to three sides in the right triangle. We then can state that triangle PQW is congruent to triangle TSW by the side, side, side postulate. Alright, going further. SAS congruence postulate, or side angle side, states if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So we have this definition of an included angle. So the statement reads if PQ is congruent to WX, QS congruent to XY, angle Q congruent to X, then triangle PQS is congruent to WXY. So we have the statement the included angle. So we have one side PQ congruent to WX, we have a second side QS congruent to XY, and the included angle is where the two sides meet together in the middle. So we have this angle here, angle Q and angle X. It's included in those two sides, or between those two sides. So therefore, it holds true with the side angle side congruence postulate. We can go further and make statements about talking about the sides, just as we did for the side, side, side postulates. Just so we know that this is true. If angle Q and angle X are congruent, then the sides have to be congruent. And then if we know that the two sides are congruent along with the other two, we have the side, side, side postulate can prove triangles congruent as well. So we know that the side angle side postulate holds just as well. Alright, let's apply these. Using SAS congruence postulate, prove that the two triangles are congruent, triangle VWZ and triangle XWY. Of course, we state what's given on the picture. We have the sides being congruent, WZ congruent to WY, and VW congruent to XW. Alright. We then can make the statement that angle VWZ is congruent to XWY. If we just talk about those two angles, VWZ is this inside angle here, and XWY, this angle here. Those are congruent because we do have vertical angles. So we know that we have those two as vertical angles. And if we take a look, we have a side, we have an angle, and we have another side. So therefore the two triangles are congruent by side angle side. Alright. Now we're going to handle a couple examples here. We have 3 examples in the next slides here on side angle side and side side side. Given MB, so the line MB is perpendicular, it's a perpendicular bisector of AP. Prove that the triangle ABM is congruent to the triangle PBM. So we can figure out a lot from our picture, and we can prove on our picture and then formally write it up. So the only given statement that we have is that MB is perpendicular bisector of AP, and we'll state that first. But what does that mean? Well, it means 2 things. First of all, it's perpendicular, which means it creates right angles. And seeing as how it's a bisector, that means that we also have sort of like a midpoint statement happening. So a bisector is like a midpoint in the fact that it cuts it up equally into 2 pieces. So therefore we can state that AB and BP are congruent to each other. And if we look at our picture, we're trying to prove that triangle ABM, the left triangle, and triangle PBM, the right triangle, are congruent. I have a side and I have an angle, considering that the 2 choices that I have to work with now are SSS or SAS. I'm going to go ahead and say it's going to be SAS. But the question is why, or the question is how. Well, if I look at my sides, I have side AB, and I have a right angle at angle ABM, and the side that's kind of connected between the 2 is side BM. Okay, and BM is in 2 triangles. If I draw them separately, BM is on the right triangle as well as the left triangle, and we know that sides equal themselves. Alright, so BM is congruent to BM, and the way we know that the sides are equal to themselves is the reflexive property. So therefore, by the reflexive property, BM is congruent to BM, and I can state that side angle side proves 2 triangles congruent. So let's formally write that up. ABM and PBM are right angles. Definition of perpendiculars, we have 2 perpendiculars. We have that they're right angles. We know that AB is congruent to BP by the definition of a bisector. Okay, cuts it into equal parts. We know that ABM is congruent to PBM, those 2 angles that were right angles by the definition of right angles. So since they are right angles, they're congruent to each other. We know that BM is congruent to BM, that's by the reflexive property. And if we have those pieces together, then I know that triangle ABM is congruent to triangle PBM by the side angle side postulate. Alright, next one. O is the midpoint of MQ and NP. Prove that triangle MON is congruent to triangle POQ. Well, midpoint, we have to define what we know here. We have the given statement, so therefore O is the midpoint of MQ and NP. What does that mean? Well, if O is the midpoint, then this piece is congruent to that piece, and this piece is congruent to that piece. I have 2 of my sides in. Now I either need to find a 3rd side congruent or the included angle. I notice I have the bow tie problem on the board, so therefore I know if a bow tie problem exists, I have vertical angles here. So then again, by side angle side, I have the 2 triangles congruent. So let's write that up formally. I have the midpoint, so MO congruent to OQ and O congruent to OP by the definition of midpoint. We have angle MON congruent to angle POQ, as we just talked about, by vertical angles. Lastly then, triangle MON is congruent to triangle POQ by side angle side. Alright, next example. Given AB congruent to CD and BC congruent to AD, prove that triangle ABC is congruent to triangle ADC. So let's mark what we have here. We do have our given, so we state that first always. We have AB congruent to CD, and we have BC congruent to AD. And I'm trying to prove triangle ABC and triangle ADC together. I have 2 methods, side angle side or side side side. If I take a look at, do I have anything in common between the 2 triangles? and I notice that I have line AC as part of both of them, so therefore by the reflexive property I can say that AC is congruent to itself, which gives me the third side that I need. So this one's relatively short, as AC is congruent to AC by the reflexive property. I then can say that triangle ABC is congruent to triangle ADC by the side-side-side congruence postulate. Okay, next example. Given AD is congruent to CB and AD is parallel to CB, prove that triangle ABD is congruent to triangle CDB. Alright, stating what we have given again for our proof and marking our picture. AD is congruent to CB and AD is parallel to BC. And we need to work with the figure in our given to prove that the triangles ABD and CDB are congruent. Things that we can note right away. We do know that BD is shared in both the triangles, so therefore by the reflexive property BD is congruent to itself, so that takes care of two of the sides. The only other piece of information that we're given is about parallel lines, and anytime we think of parallel lines I would recommend looking to see if there's a Z involved, or where are the two lines and where the transversal that goes across those. So AD and BC are parallel lines, and if I connect BD here, I do have a transversal that's cutting across those two, and when I have a transversal I notice I have the Z. Okay, and I have the corners here of the Z, so I highlight just the black. I notice I have the black Z, and I have the angles in there that are congruent by alternate interior angles, as the corner of the Z imply that. So therefore then, by side, angle, side, the two triangles are congruent. So let's write that up formally. Angle ADB is congruent to angle CBD by alternate interior angles theorem. Please note that they are needed to be three letters for the angle, as you cannot just write angle D, as there's two angles that come from D. So we have the angles congruent. We also have DB being congruent to DB by the reflexive property. So from those two statements and our given, we know the triangles are congruent by side, angle, side. Alright, that ends lecture for today. Problems that we're going to go over in class, we're going to practice on, are from page 266, 4, 12, 13, 15, 21, and 25. And just to clarify the directions, we're going to prove only the triangles congruent on questions number 4 and number 15.